Okay, friends, 7.3. These are a little bit different. Up until now, when you were dealing with the first set of rules, you were able to take things that you know and conclude something else. Now it's a little bit different. These rules of replacement, you'll notice it's called rules of replacement here. What this says is these statements for each one, in this case for De Morgan's, not both P and Q, can be replaced by not P or not Q. The idea is here, these sentences or these statements are what we call truth functionally equivalent. They are made true or false under the same conditions. So, for example, with De Morgan's, this first statement here says, it is false that P and Q, or in English, it is not true that you have both P and Q. Well, if you don't have both P and Q, then you either, don't have P or you don't have Q. If you don't believe it, draw the truth tables. Remember chapter 6? Haunting you again. If you draw the truth tables, you'll find that these two statements are true under the same conditions. Same thing here. Incidentally, De Morgan's, very important rule. You're going to find in 7.4, there's another one called transposition. It's also very important, and what makes them such important rules is that it allows you to go from an and statement to an or statement, or vice versa, from an or statement to an and statement. Being able to get the statement in the form that you need to use another rule is what you're going to need to be able to finish off these proofs. I have no illusions, these are tough. Let me run through these rules really quick. I'll give you some examples in another video, and hopefully we'll simplify things at least a little bit. So for starters, De Morgan's. And if you have your little sheet with the rules, man, you want to highlight or circle De Morgan's or something because you will be using De Morgan's or transposition frequently. My advice to you is when you're constructing a proof and you get stuck and you don't know what to do, try De Morgan's or transposition. 9 times out of 10, it gets you the kind of statement you need. But here's how they work. De Morgan's, as we said, the first one, you see there's 2 versions of it, whatever. If the combination P and Q is false, then it's either because you don't have P or you don't have Q. You may not have either one of them. Remember, for an or statement, if either one or both are true, then your statement is considered true. It also works the other way. This says not either P or Q, or in English, neither P nor Q. Well, if you don't have P or Q, then you don't have P and you don't have Q. Again, who cares? Well, you care because you still have a few more weeks left in this class, but also remember that you can use simplification to simplify out 1/2 of an and statement. So if you have this weird or statement like this, and you want to just say, I know that P isn't true, or I know that not P is true, however you want to say it, if you use De Morgan's to change it to this, then you can simplify. So that's how these rules work. Big, big, big deal, De Morgan's. Huge, huge, huge. Commutativity, dumb rule. What commutativity says is if you have a statement that says P or Q, you can switch the letters and call it Q or P. Problem is you have to use this sometimes in order to finish off a proof. It's not a very compelling rule. We don't really learn anything new. We know that if P or Q is true, well then Q or P is true. It's the same thing, right? Same thing with and. If you know P and Q, then you know Q and P. Boring, but you have to use it sometimes because remember, for example, the simplification. Hurley is only going to let you simplify the first term. So if you have P and Q, you can simplify out P, but Aplia is not going to let you simplify out Q until you put the Q in front. You say, that's cheap, that's irrelevant, how dare they, or whatever it is you say. I agree with you, too bad for us, because that's the rule. Associativity, kind of fun, because you get to say ask. All this does is it allows you, in a statement that is a bunch of ors, remember that a well-formed formula, a WOF, can only contain 2 terms within the parentheses. Well, this is a bunch of ors, as you see. So this says P or Q or R. And this says that's the same as P or Q or R. Again, not very compelling. however, might be important because we have to do something like a disjunctive syllogism where we know that one of these disjuncts is false, so we can conclude the other one. So all associativity allows you to do with this kind of a complicated or statement or a complicated and statement, it allows you to take the parentheses and move them. That's all. Nothing very exciting. Again, De Morgan's is the big one that you have to probably struggle to understand a little bit better. These are really just kind of ceremonial, that's not the right word, procedural, where we can move the parentheses from one group to another, or we can switch the order of terms. Distribution, there's actually work here. There's a little bit more that it can do. But as you see, what the first statement here says, P and Q or R. That means P is true and either Q or R is true. So if you know that that's true, if you know that P is true and either Q or R is true, then you could conclude either P and Q or P and R. We already know P is true. That's part of our and statement. So it's either P and Q or P and R, and that's what this says. Again, going to become useful to you when you can, if you have a statement like this, when you change it to this, maybe you can use disjunctive syllogism to get one of those phrases by itself. Same thing with distribution. If you know that you either have P or you have Q and R, then it's fair to say P or Q and P or R, which now we could use to simplify out one of these terms. So a lot of these just set you up to use one of your other rules. Just to walk back through that briefly, either you have P or you have both Q and R. So you have P or Q, because you either have P or both of them. P or this, and P or that. That is all. Finally, in 7.3, double negation. Almost as worthless as commutativity, but another one that we have to use in order to finish off the proofs in Applia. It is technically a rule, it is a bit of a technicality, but you're going to have to use it to get the answers. So what this says, and you already knew this, it's kind of like multiplying with negatives. You know how negative times a negative is a positive? Well, that's kind of what this says, right? Two negatives makes it a positive. If you know that P is true, then it is false that not P. Or if you prefer, it is false that P is false. All of these rules in 7.3 and 7.4, the rules of replacement, work both ways. If you start with this, you can change it to that. If you start with this, you can change it to that. That's a good thing. It actually kind of seems like it's maybe a little bit more complicated, but it's a good thing for you in the end because it gives you a lot more flexibility in how you can come up with these proofs. Sorry to have taken so long in this first section. This is kind of a big deal. So I'm going to run through the other one in a minute, and then I'll give you some examples.